Welcome to our deep dive into one of the most fascinating technologies of our time, quantum computers. These machines promise to solve problems that classical computers, even the fastest supercomputers, would take millions of years to tackle. But how do they work, and why are they so powerful? Today, we're going to explore the principles behind quantum computing, how it differs from traditional computing, and the challenges that scientists face in making it practical. To understand quantum computers, we first need to understand how classical computers work. Classical computers operate using bits. A bit can be either a 0 or a 1, and all the information in a computer is ultimately represented as sequences of zeros and ones. When a classical computer processes data, it manipulates these bits through logical operations, and the sequence of zeros and ones produces the output we see. Quantum computers, on the other hand, use something called qubits. Unlike bits, qubits can exist in a state of 0, 1, or both 0 and 1 at the same time. This property is called superposition. Imagine a spinning coin. While it's in the air, it's not strictly heads or tails, but a combination of both. Similarly, a qubit can represent multiple possibilities simultaneously. This is one of the key reasons quantum computers can perform certain calculations much faster than classical computers. Let's explore superposition a bit deeper. When a qubit is in superposition, it holds all possible states at once. If you have two qubits in superposition, they can represent 4 states simultaneously. With 3 qubits, 8 states, and so on. The number of states grows exponentially with the number of qubits, which means a quantum computer with even a few dozen qubits could theoretically handle more possibilities at once than all the classical computers in the world combined. However, qubits don't stay in superposition forever. When you measure a qubit, it collapses to either 0 or 1. This is why quantum algorithms must be carefully designed to increase the probability of getting the correct answer when the qubits are finally measured. Another fundamental concept in quantum computing is entanglement. When qubits become entangled, the state of one qubit is directly related to the state of another, no matter how far apart they are. If you change the state of one qubit, the other qubit's state changes instantly in a predictable way. This allows quantum computers to link qubits in complex ways and perform operations that would be impossible with classical bits. Entanglement is essential for many quantum algorithms and also plays a role in quantum communication and cryptography. In classical computers, we use logic gates like AND, OR, and not to manipulate bits. Quantum computers have quantum gates, which manipulate qubits. Unlike classical gates, quantum gates can perform operations on superpositions of states, allowing multiple calculations to happen at once. These gates are represented as mathematical operations called unitary transformations, and they form the building blocks of quantum circuits, which are the quantum equivalent of classical computer programs. So why are quantum computers so powerful? It's not that they are faster at every task, but for certain problems, they can provide exponential speedup. Problems like factoring large numbers, simulating molecules, optimizing complex systems, and searching through large datasets could be solved in minutes or hours on a quantum computer, whereas classical computers might take thousands or millions of years. This potential is why tech giants, startups, and research labs are investing billions in quantum computing research. Despite the promise, building a practical quantum computer is extremely challenging. Qubits are delicate and can easily lose their quantum state due to interactions with their environment. This loss is called decoherence. Even small disturbances like heat, vibration, or electromagnetic noise can destroy the information in qubits. To overcome this, scientists are developing quantum error correction methods and using techniques like superconducting qubits, trapped ions, and topological qubits to protect and stabilize quantum information. Right now, quantum computers are mostly experimental. Companies like IBM, Google, and IonQ have built quantum processors with dozens or hundreds of qubits, but these machines are still limited by noise and error rates. Researchers are also exploring hybrid approaches, where classical computers and quantum computers work together to solve problems more efficiently. As the technology improves, we may see quantum computers tackling real-world problems in chemistry, finance, logistics, and artificial intelligence. Quantum computing is a fascinating blend of physics, mathematics, and computer science. Its principles, superposition, entanglement, and quantum gates, allow it to explore multiple possibilities at once, offering unprecedented computational power. While practical, large-scale quantum computers are not here yet, the progress being made every year brings us closer to a new era of computing. Imagine solving problems that were once considered unsolvable, unlocking new materials, curing diseases, and even advancing artificial intelligence. Quantum computers may not replace classical computers, but they will redefine what's possible in computation.